Hello everyone, my name is Wesley Dimery and I am part of Team 2 together with Madison Muldoon, Haley Stafford, Dwan DePoe, George Hernandez, Brenna Garza, Valerie DeWalt, and Esteban Schrick. We are presenting today on the thermodynamics of NASA's James Webb Telescope, a modern marvel of engineering ingenuity. A little bit of background on the project. It started its designs in 1996 and was worked on for almost 25 years before it was launched in 2021. And then on January 24th of 2022, it arrived at its final orbit around the second Sun-Earth Lagrange point, also known as L2, which is approximately 1 million miles away from Earth, as seen above. It weighed about 14,000 pounds before it launched, and it is currently the largest optical telescope in space. It was named after the administrator of NASA from 1961 to 1968, James Webb, who worked on the Apollo missions, and it has cost about $10 billion. Before we go into the thermodynamics of the James Webb Space Telescope, I wanted to show you all a couple images of the same image, except on the right side is an image from the Hubble telescope, which captures mostly visible and UV light, and on the left is a picture from the James Webb telescope. It captures mostly infrared light, which means it can capture images from much further away. So you see a lot more stars, and a lot of those are actually galaxies. They're on the left, so it's really amazing and beautiful, the images we've been able to capture using the James Webb telescope. Here is a schematic of the James Webb telescope showing the sun shield at the bottom, which reflects away a lot of the radiated heat from the sun, so that side is always facing the sun while it's in orbit. And on the other side is the telescope itself with the 18-part mirror, which acts as one, which actually captures the images. And this side needs to be kept below 35 Kelvin. There are four major components that are used in the imaging system of the telescope, including the NIR cam, the near spec, the FGS, and the MIRI. However, these need to be kept very cold at temperatures of 35 Kelvin and below, which we will go into more detail later on in the presentation. So I will pass it off to Maddie for more of the background.
The purpose of the telescope is to find early galaxies formed from the Big Bang, as well as newly forming stars that are forming more planetary systems. How it does this is by detecting distant infrared waves. We know the farther away an object is from the Earth, the more it shifts to the red side of the spectrum. The components that actually detect these infrared signals are the ISIM of the James Webb Telescope. Part of the ISIM is the MIRI, the mid-infrared imaging and spectroscopy, the NIR cam, which captures images of the galaxies, the NIR spec, which detects near infrared, and as well as FGS or TF, which is the tracking system of the telescope used to find the mirror. The problem about these components is that since they detect infrared light, which we know is correlated with heat, they are very sensitive to heat, and they thus require optimal temperatures ranging from 35 K down to 6.7 K, which requires some cooling mechanisms.
Two particular types of cooling are passive and active cooling. Passive cooling is a method of cooling which doesn't require any external power source or mechanical components. And some examples of this are shade, insulation, phase change, and ventilation. While active cooling is a cooling system that does use mechanical components or an outside power source. Some examples of this are fans, pumps, or a refrigeration cycle. Some of the pros of active cooling are that they are more efficient compared to passive cooling, but passive cooling systems can be a little bit more simple than an active cooling system.
Of the four main components of the James Webb, three of them can be cooled using the passive cooling system, which was designed to be self-regulating and requiring only minimal energy. The sunshield, radiators, insulation, and the strategic orientation of the telescope itself help to keep the instruments and detectors cold. The insulation, made up of multi-layer insulation blankets, serve as a barrier to trap and control the heat. The radiators, made of aluminum, are strategically positioned to radiate the excess heat away from the spacecraft's electronic instruments.
Another aspect of passive cooling systems that the telescope uses is the sun shield. The sun shield is always orientated to where it is between the sun and other external heat sources and the telescope. The purpose, as detected by its name, is to block the heat from the sun and earth from reaching the ISIM components of the telescope. It is extremely huge. It's roughly tennis court size, and it's 21.197 meters by 14.162 meters. It's made up of 5 layers that will gradually experience a lower amount of heat as it goes towards the ISM, because in between each layer, heat is dissipated. As regarding the material of the sun shield, it is made of kapton, and this basically mitigates the risk of the hotter layers of the sun shield from expanding and the cooler layers of the sun shield that are closer to the telescope from shrinking. It is coated with aluminum, which is highly reflective and reflects the sunlight and the sun rays, as well as doped silicon coating, which increases the emissivity of the telescope itself. As we can see from this equation, we have the heat being emitted by radiation, and as you have a higher emissivity, you also have a higher amount of heat being radiated off of an object. Going back to the area of the sun shield, because it is so large, we also have a larger surface area as indicated by the equation, and we can see the larger surface area you have, also the higher amount of heat is being emitted from that object as well.
So the James Webb Telescope requires an active cooling unit for the mid-infrared instrument, otherwise known as the MECE. The MECE detects mid-infrared light at wavelengths from 5 to 28 microns. It uses 3 arsenic-doped silicone impurity band conduction detectors, which need to maintain a temperature of 6.7 Kelvin or less to operate properly. An external cooling mechanism called a cryocooler is utilized to increase the heat transfer out of the system. The cryocooler is comprised of a pre-cooler and 2 pumps, which use helium as their working fluid.
To reach the minimum temperature of 6K, the MECE uses an active hybrid 4-stage cryocooler. The primary piece of this cooling system is a pre-cooler or a cooler compressor assembly, a thermally coupled 3-stage post-tube cryocooler that reduces the temperature to 10K. The post-tube refrigeration process relies on thermoacoustic to transfer heat. During compression, sound waves through the helium gas create a pressure change in the thermoacoustic stack, causing a temperature gradient in the low conductivity stack. This gradient is cool the helium working fluid to dispense it to space. The next step is to take this cool fluid and transport it to the cooling tower assembly. This separates it from the CCA and the CHA, the cold head assembly. This region consists of the JT compressor valve that brings the temperature down to the 6K of the final pressure. This region is controlled by the cryocooler electronics assembly.
In conclusion, the James Webb Space Telescope utilizes both active and passive cooling to achieve the necessary temperature constraints of the components used. For the passive cooling, we went over the sun shield and radiators, and for the active cooling, we went over pre-cooling and cryocoolers. The addition of an active cooling system allowed the James Webb Space Telescope to use more advanced mechanisms to collect the amazing photos we saw in comparison to the Hubble telescope.